Hi everyone, I'm Ganluo, and today I'm going to talk about Huffman encoding, and I will talk about its principle and its C++ implementations. Huffman encoding is very interesting since it uses a lot of data structures like trees, like priority queues, like map, and it's also involved like the tree serialization and deserialization. So it's very useful. For example, in my previous interview, some interviewers asked me like some problems about encoding. Like we just chat a little bit, and I say the most naive encoding algorithm is row length encoding. For example, there are 5 consecutive ones, and we could encode something like 1, 5. Like since there are 5 continuous consecutive ones, so I will encode 1, then encode 5. Maybe we need some separator between 1 and 5. And I would say, and there's also a greedy algorithm called Huffman coding. It's very useful, and I will talk about its like implementations. And the interview, he will recognize you. Okay, so let's see. We use ask coding encoding code a lot. Each character like A, B, C, D, E, they are 8 bits, so they're fixed length. And for Huffman coding, it's invented a long time ago, and it's very useful. The principle behind it is some statistical coding. And since in our data in one text, not all characters occur with the same frequency. For example, some characters occur a lot. Sometimes some characters like Z, they are not very common. So we can use some like encoding to use less bits to encode the most frequent character. The Huffman encoding workflow is like this. First, we scan our text, then we count then we build a frequent map, like how many times, how much frequency of A, how much frequency of character B, and C, D, E. Of course, we need to include all characters like space, like comma, like dots. Then we can put this node in a priority tree. Then we use this priority tree to build a Huffman priority queue to build a Huffman tree. Then we can build a encoding table from this Huffman tree. Then we can write our encoded data to a separate file. So the most important thing is how to build a Huffman tree. We can consider the following short text. First, we need to count the occurrences of all the characters in this text. So we can use a map to track. Of course, we need to include the space. That's our frequency map. For example, you say the uppercase E occurred 1 time and the lowercase e occurred like 8 times. Okay, next we need to create a tree node for each of the characters in this frequency map. Then we can place this node in a priority queue, and we need to pass a comparator to this priority queue. The lower will be in front. We have this Huffman tree node, and we have 3 fields, or 4 fields. The first is a character. The real character is our leaf node, and the real characters non-leaf node, they only contain the frequency. Later, I will show how it looks like. Of course, the node has left children and right children, and we also have a priority queue. So first, we place all these nodes into the priority queue. So since we pass a specific comparator, so we can play. So the the node with low frequency will in the top of the queue. And the algorithm look like this. Let's just go through the process. First, we dequeue the first two elements in this priority queue. Then we create another tree node. The character that doesn't care. We only care about the frequency of the tree node. So the frequency of this tree node is the sum of these two children's. Then we insert it back to the priority queue. Then we do it again and again. Pop, insert, pop, insert, pop, insert, pop, insert, pop, insert. Did you notice that the character with a low number of occurrences, they're at the very bottom of this tree? It's like the depths of this node, they're very deep, they're very high, like the depths, like the uppercase E, I, Y. But for example, for space character, its frequency is 4, but the depth is not that high. Okay, let's continue the process. DQ, InQ, DQ, InQ, DQ, InQ. Okay, now there's only one node in my priority queue, so we can get this node from the priority tree, priority queue. That's my final Huffman tree. Okay, now we can generate the encoding table from this Huffman tree. For example, what's the new encoding? What's the new encoding like of this uppercase E? Let's say how we can go to this node from the root node. We go to left, go left, go left, go left. We define go left is a 0, go right is a 1. So it's 0, 0, 0, 0. So the coding of uppercase E is 0, 0, 0, 0. So what's the coding of the lowercase e? It's go right, then go left. So the coding of the lowercase e is 1, 0. So we can generate this new encoding table. Example for space is 0, 1, 1 space. Then use this encoding table, we can encode the original text. The uppercase E is 0, 0, 0, 0. Then the lowercase e is 1, 0. So we can iterate every character in my original text. Then for each character, we can look up the encoding table and find the new code and write this code to my text. Of course, it's the write is a bit stream, not byte stream. We know that we can only write a byte to a file. We cannot write a bit. So we need a buffer. Like first we write 4 bits into this buffer. It's a character. Now we use 4 bits in this character. Then we write some other characters. Once the buffer becomes 8 bits, we can write this byte to the file. I will explain later in my code to show how the bit stream works. So there's a very important question. Why there's no need for separator character? For example, this is the encoded data. How do we know? Like for example, like for first 0, it's it's an encoding of a character, or it's a prefix of some other characters. So for Huffman encoding, it's not a prefix encoding. This is very important. The coding is very unique. Let's go through this example. Let's say the lowercase e. The code is 1, 0. So do we have 1, 0, 0 or 1, 0, 1? No, there's no 1, 0, 0 or 1, 0, 0, 1. So if it's 1, 0, then we know it must be E. Since there are no other characters the prefix is 10, oh, right. Same for 011 space. There's no other character whose code start with 011. So it's not prefix coding. It's very unique. Huffman encoding is not prefix coding. We can also see from this graph, all the characters, their leaf node with them for this E. It's 1, 0. So if we have 100 or 101, E will have children, so E will not be a real character. For each real character, there's a leaf node, so they don't have any like children. So the coding is unique. So we don't need a separator character. So originally each character the 8 bits, the fixed length, but now each character is encoded with less bits. Okay, how do we decode the file? Like we write this encoded data to file. How do we decode it? Of course, we need the tree. If we have trees, the decode is very simple. For example, we have 00000 at first. How do we decode it if we have tree? Okay, 0 go left, 0 go left, 0 go left, 0 go left. Okay, it's a leaf node, so we know it's a character. We got uppercase E. You find that the tree is very important. So we also need to write the tree into our encoded data. So the encoded data consists of two parts. First, we write, or we can say we serialize the Huffman tree into this encoded data. Then we write the real encoded data to the file. So the file has two parts. The first part is the tree. The second part is the data of the text. Yeah, this is what I have talked previously. Okay, so let's take a look at the code. The implementation is in C++. And this is my GitHub, and this is my implementation for Huffman. I wrote this code about 8 or 9 years ago and submitted it in GitHub about 5 years ago. So I have two components. The first component is about binary read and write. Let's take a look at the binary write. So the binary write has some public API called open a file, write a bit, write a character, and write integer. And it also has some private field. The first is buffer. For example, we may write 4 bits first. So it will use 4 bits in this buffer, and I will set n to 4. Then I may write 5 bits. Then for the 5 bits, I will write the first 4 bits of the 5 into this buffer, then n will become 8. Then I will write this byte into the output. Then we also have 1 additional bit. Then I will write the additional 1 bit to this buffer, and n will be 1. Let's say the implementation of the binary std out. So this is the implementation of the write bit. First, I always write the bit into the last bit of this character. So every time I write bit, I will move the buffer to the left, the bit operation. And if the bit is a 1, then I could write this 1 to the last bit of this buffer. Otherwise, it's 0, so it's a no op. Then I plus auto increments n. If n is 8, which means I used all the bits of this buffer. It's a character, so it has 8 bits. If n is 8, then it means all the 8 bits are used. I can clear buffer. Clear buffer is very simple. Just reset n. Then we can write this buffer like to our output. Then resets the buffer as well. Write characters implementation is also very simple. If n is 0, which means we can write this whole character into the output. We can write a new, like the whole byte. Otherwise, I can just reuse the implementation of the write bits, since there are 8 bits in this character. So I can just write 1 bit 8 times. Okay, let's see the implementation of the Huffman encoding. So Huffman encoding, as mentioned, we have 4 fields: the left children, right children, and we have frequency. I call it weight here. And we also have character, and I also provide some constructor. And I have helpful function called isLeaf. Oh, and I have this comparator, which is for the priority queue. This is Huffman encoding table, for example, for the uppercase E, it can be 0, 0, 0, 0, 4, 0. So I use a vector of Boolean, it will be false, 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 false. We have Huffman tree, and also have the binary std in, std out. And the public API is very simple, just encode and decode. For encode, we need the original data, and we need a file to write. For decode, we just decode the file and return the original data. Let's see the implementation. So here, let's see how we built the Huffman tree. First, we have the frequency map. Then we just iterate every character in our original data to build this frequency map. This is for debugging only, so we can output some useful data. And we have this priority queue, and we just enqueue my initial node with frequency. While the size of the queue is greater than 1, like we always dequeue the top 2 elements, then we create a parent node. The frequency of the parent node is just the sum of its 2 children. Then we push it back to the priority queue. When we here, which means the size of the priority queue is only 1. So the node is a Huffman tree, the root node. Then I use this function to build the encoding table. We just use DFS to build the encoding table. You can take a look later. Of course, we need the write try function, since we need to write the try to maybe we can just call it write tree. We can write the Huffman tree to the encoded data. Then we write the real data of the text file. So there are 2 parts. The write try is just serialization of this tree. So there are many like coding questions in LeetCode or other platform like ask you to like serialize and deserialize the tree. So this implementation is very simple. If it's a leaf node, we write 1 bit true. If it's not a leaf node, we write 1 bit false. And if it's a leaf node, we write 1 bit true. Then we write the character. Otherwise, we write false. We write the left, then we write right part. And we also need to retry. First, we read the bit, so we know if it's a leaf node or not. If it's a leaf node, we just return a tree node. And we need to read the character of this node. Since it's a leaf node, so it's a real node. Otherwise, it's not a leaf node. we need to recursively build the left children and build the right children. Those write, try, and retry, and this is how they work. The code is very short, but it involves some like recursion logic. Let's see how encode work. First, we build Huffman tree. Then we initialize the binary std out. Then for the encoded data, we write try first. And here I also write a very simple integer to indicate like how long is my data. It's not very necessary. Now I can just iterate every character in my data. For each data, I have the code. Then I just, for example, the code for uppercase E is 00000. So I just iterate it 4 times. Each time is always a false. And just write the bit 0 4 times. Okay, let's see how decode works. Decode first we initialize the binary std in. Then we use this retry to read the Huffman tree we write to this encoded data. Then we read this length. Okay, now I just iterate length times. Each time I just go through the tree. When it's a leaf node, I know the character. Then I just append this character to my data. Finally, I can just return the data. So that's how the implementation look like in C++. If you have time, you can read the code and try to implement yourself, or you can reference my code. Here I have a simple, like I have some tests. You can just run make if you are using Unix, Linux, or Mac. Okay, so that's how Huffman encoding works. And sorry, my English may not be that good and not very fluent, but yeah, thank you for your time. Thank you.